Did somebody just people? No. We're good to go. I think the crowd. Okay, awesome. Let me. Great. Thanks for joining today. I'm very honored to have Professor Neer join us from MIT. Also, actually, Neer is also a co-founder of Neural Magic. So, technically part of the Red Hat family. Very, very welcome there. So typically, if you've been attending random samples, we sort of overfit to the generative AI world, talk a lot more about language model papers. But today is going to be really, really interesting. So we're going to take a step back. And what Neil would do is, through his new paper on which is titled Towards Combinatorial Interpretability of Neural Computation, take us back to understanding how neural networks actually work. It's sort of interesting for me because I was just talking to Neil earlier about the last time I was in a talk where we sort of went deep into the world of deep learning and how neural networks actually work was roughly 8 years ago. So I'm super excited to understand what sort of theoretical advancements we have made in the field and are we in a better position to better understand neural networks. So without any further ado, Professor, please take it away.
Thanks, Akash. Hi, everybody. So this is joint work with Mika Adler, Dan Alistair, and myself. So Dan and I actually work for Red Hat AI. So, and Mika is a colleague of ours, a consultant for Neural Magic who just is a visitor at MIT right now. So this is our joint work. What I'm going to talk about is work in the field of mechanistic interpretability, right? And the question that mechanistic interpretability tries to answer is really, how do neural networks work? And of course, there are a lot of reasons that we care about this. Safer AI systems, everything that has to do with transparency. But also, if we actually understood how they worked, we could do sparsification better and quantization better and everything much better, right? And then there is the intellectual question that is my driving thing, which is to understand intelligence, and neural networks are, to my mind, an intelligence, a form of intelligence, and we just have to kind of understand it, maybe on the path to understanding other things. So that's kind of the driving force here. The prevailing way of thinking in this field about neural networks is that they compute using features, essentially ways of representing concepts, right? And so I'm gonna use that view. That view is going to be central to how I think about neural networks. And when we want to ask, okay, so why is it challenging to interpret what a neural network is doing? Okay. I'm going to assume that everybody here knows a little bit about neural networks, right? So I'm not going to get into simple explanations, but just think of it, in terms of neurons, right? We kind of know, right, that every neuron is participating in the computation of multiple concepts, and because of that, right, it's kind of hard to understand exactly what every neuron is doing at any moment, right? So that's called polysemanticity. So that's one problem. The other thing is what we call the superposition hypothesis. This is something raised by the guys at Anthropic, right? The idea is that training of a neural network packs many more features than neurons into the network, right? And so what the network is actually doing, right, is trying to represent, right, these many different features in an efficient way, right, by kind of partitioning the activation space into ways that allow us to pack as much as we can. Okay, and this is kind of how people think about this field. Great. So what's the current state in mechanistic interpretability before this work that I'm going to present to you? Well, people are focused on the geometry of activations. If you've heard this concept before, it's the idea right, that you can think of the activations of a neural network as some high dimensional space, and we're trying to understand what these different vectors mean, okay? And the techniques used for understanding this is to use sparse autoencoders, transcoders, right, and look at the activations, and by tracing the activations, right, we can actually, kind of isolate features, right, and look at what these features are actually reacting to, whether it's the Golden Gate Bridge or something more complex, right? And beautiful stuff has happened with autoencoders and transcoders, and we actually, in real production networks, get really beautiful views into what actually a given neuron is doing, okay? But apart from some really kind of recent work that is a little bit more interested in the relationship between features, there really isn't an explanation of what the computation actually is. So what's the logic going on here? Okay, so I've got these features, right? I've got all these features, but how do they relate, right? How does the Golden Gate Bridge relate to other things, right? That the network is responding to, okay? So this is our goal, okay? We want to actually understand what the logic of the computation of a neural network is, okay? And the way we're going to do this, which is very different from what's been done in the past, is we're actually going to look at the parameters, okay? Which sounds a little crazy, but I'm going to show you that it's not, okay? Okay, cool. So the new focus is going to be combinatorial structures that are encoded in the weights and biases of a neural network. Okay, and we're going to look at something at a simplification. Okay, the simplification is going to be what I call a sign-based categorization. I'm not going to look at the directionality and activation space. I'm just going to look at whether the weight is positive, negative, or zero. Okay, and we're going to simplify it in another way. Okay, we're just going to look at Boolean expressions. We're not going to try to do what a large-scale neural network does, right? But we're just going to focus on learning Boolean expressions. This is going to prove to be meaningful, right? It's going to give us control over what we actually train for, right? And we're going to be able to actually understand things because of that, okay? And that's what I aim to show you. So the goal is to explain how features are computed and represented, okay? I want to explain to you polysemanticity and superposition, okay? And hopefully, in this talk, I can actually kind of show you a little bit of our understanding of what scaling laws are and things like that when you actually look at the computation, okay? All right, so with that, I'm just gonna, let me just delve right into it, okay? So I'm gonna use a very simple neural network, okay? Here's my neural network, okay? I get my input, right? I have a layer 1 matrix, right? If there were m features here, there will be m features here, okay? And then I'm going to have n neurons. Then I have a bias, a ReLU after the bias, and in the second layer, I just have a single neuron, sigmoid, and Boolean answer. Okay, really, really simple network, okay? And let's just say that I want to hand code this network. Here's what I want to do. I want to compute this simple Boolean expression, right? It's a disjunctive normal form that has 3 clauses, okay? And so all I want to do is be able to code this into the neural network. So it'll compute this expression, okay? So let's see how I would do that, okay? So I'm going to suggest one way to do that, okay? So think of it like this. I'm going to do what we would call monosemantic coding. Every neuron is going to compute one clause, okay? So let's take here neuron 2, okay? I have neuron 2 to compute the clause x2 and x4. So how would I do that? Well, okay, using, ReLU and bias, the way to code x2 and x4 is to say, okay, I do the ReLU of x2 plus x4 minus 1. Okay, you can think about that yourselves, right? So if either of them, is 1 but the other isn't, then I get a 0. But if both of them are 1, then I get a 1 out of this thing. Okay, so if I just now want to actually do this coding, all I need to really do is this. Okay, I go to my matrix and I put in column 2 and column 4, right? I put 1s, and everything else in the column is 0, so that when when this vector is multiplied here, right, it'll hit the 2 1s, and I'll get a 1 here, right? And I'll get 0 every other place. Then I do the -1, and boom, after the relo, I've got my value. Okay? Kind of, everybody okay? Pretty straightforward, right? Okay? So that's how I would code, this one feature with one neuron. Okay, great. Let's say I have another one here, it's X3 and X6, okay? So I pick another neuron, right? And again, I do the same exact thing for that neuron. Okay, great. So of course I can continue to do this, right? But I run out of monosemantic neurons. I run out of neurons, right? After 8 features, I'm done, right? So what do I do as the number of features increases, as I become polysemantic, okay? I've got to come up with a coding scheme, okay? And here's an example of a coding scheme. So what I could do, right, is the following, right? To represent, X2 and X4, I would represent it not with 1 neuron, but with 2 neurons, right? Each of them doing exactly the same thing, right? And now, the signal, the channel that comes out of this, that is passing this information to the second layer neuron, right, are essentially the kind of the outputs of this and that, and that's my X2 and X4. Okay? And if I want to do, X3 and X6, right, then again, I just use these two. And you notice that they're not overlapping, right? And because they're not overlapping, it's still very obvious what the outcome is here, right? How I'm coding here, okay? But of course, as the number of features goes up, right, I'm going to eventually, right, reach a situation where, like, if I do X7 and X9, now I have to start using neurons that I've already used before, right, for the new code, for these new coding these new features. And so what do I do about that? Well, what I want to do when I'm doing this, right, what I'll just do, right, is make sure that even though the features overlap in some neurons, there are other neurons where they're not overlapping. So that the channel actually manages to pass a signal for my feature, even though it's overlapping in some places, there's always places where it's still getting through. Okay? So kind of that's the idea. Okay? So I've just hand-coded a neural network to compute this expression. Okay? Sound right, right? Okay. Questions so far? Anybody? Okay, so we have our hand coding.
Oh, I do have a little question. Really
Yeah,
quickly,
sure.
if that's okay. So I guess it would it be correct to say one of the takeaways here is like you can keep adding more features and sort of reusing things, but to a point, I guess.
Yes,
and
to a point.
And that point is sort of.
And here's the point. Thank you for, I didn't plant that. And the point is this, so theorem, Mika Adler and myself, we proved this last year, okay? So you can add, like for the AND operation that I showed you, you can keep on adding features, right? And as long as you have, for M, if you want M prime features, okay, that is you want to code M prime features like that, right? Then you need essentially root of M prime, log of M prime neurons, and M prime log square M prime parameters. So we show an algorithm that does that, that does this coding with this number of neurons and parameters.
Is this like a lower bound?
No, this is an upper bound. This is an algorithm, right? And there is a lower bound that we prove also. We prove based on kind of an information theoretic argument. We show a very close lower bound. In fact, you can't code, M prime features, right? If you have less than, omega, of M prime log M, root of that, neurons and M log M prime parameters. This thing is kind of really super interesting. This is saying that if I want to code M prime features, okay? I need essentially a linear number of parameters. The number of features that a neural network can code is linear essentially in the number of parameters. Now this is kind of crazy because you know, if I just wanted to represent the feature in the network from Johnson-Lindenstrauss lemma, I know that I can do this with logarithmic number of bits essentially, right? So this is the difference between computing, right, and encoding. So to compute in superposition, I actually can only, I need a linear number of parameters, even though I need exponentially less if I just wanted to represent these features. Okay?
Is that bound, lower bound, based on particular architecture or?
No. This is a general information theoretic, any network. Any network.
Without the constraint that we're here only considering sort of
Boolean.
binary.
No, it's an actually what it's talking about is that I need omega of n prime log n prime bits.
Okay, so it is.
For any architecture. Any architecture. Kind of crazy. And the fact that we achieve coding by hand to do this is kind of surprising. But that's not, yeah, go ahead.
Sorry. This is awesome. I've been looking at this for years trying to figure this out, so this is really cool. But also, I've seen in practice, like it's super hard to get this. Like if I try to code a neural network and try to actually get it to represent my data in a specific, in max or optimal way, you know, like using the number, like assuming there's like a max number of features that I'd like to represent my data with, you know, I can kind of design that architecture and then, you know, I start the gradient descent process, but like most of the time, I'm never going to be able to represent it that efficiently. You know what I mean? Like you can do it by design. Here.
Let me show you. So fair enough. I can do it. I am doing it by design.
Right.
But that's not really what I want to talk about. I'm agreeing with you.
Gotcha.
Okay.
I was curious if you had any like techniques for getting this in practice, or if that's for
That's what I want to show you.
Okay, amazing.
Yeah. So that's what I want to show you. Not that I know how to design a specific thing, but I can show you.
Mhm.
So let's go back to the same exact problem again. Okay. This time I'm going to do it with stochastic gradient descent. I'm going to actually train my neural network. Okay. So I'm going to train the network for, you know, m equals 16 and n equals 16. So 16 variables, 16 neurons, 30,000 random inputs, you know, atom optimizer, 2,000 epochs. I'm going to train the neural network.
And this is randomly initialized?
Randomly initialized. Okay? And I train the neural network. Okay, here is what I get. Okay, so the expression that I trained for is this, x3 and x11, or it's just randomly generated expression, x3 and x13, x2 and x6, blah, 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 blah. Okay, all this, okay? And what you see here, this is W1, this is the weight matrix 1, this is the bias that I showed you, and this is layer 2, but standing upright, okay? You look at this and you say, well, Amir, thank you very much. That's very interesting. But okay, so what, right?
Mm-hmm.
Maybe you see that, okay, Amir, this neuron is dead. Okay, that's obvious, you know. Okay, but let me do some manipulation on this. Okay, so let me just do the following. Okay, all I did now is sort the columns based on the expression. So I put x3 and x11 next to each other. And I put x9 and x13 next to each other. And I put x0 and x4 and so on and so forth, okay? Do you see that something's showing up here? Some stuff is happening, right? Some stuff is happening here. Okay, so let's push this one more step further, okay? So what I want to do now is I just want to look at the positive, at the neurons that have a positive layer 2 weight. Okay, so I'm throwing away everything that has negative layer 2. I'm just looking at the positive layer 2. So these are the things that when I get through the sigmoid are going to give me a 1, right? A positive response. I mean, look at this thing. X3 and X11 are the same, right? What's happening here? Well, what's happening here, this is with gradient descent, I didn't do anything here. I just trained the network, Okay, look, it's positive, positive with a negative bias. Positive, positive, negative bias, positive, positive, negative bias, right? It's essentially doing ReLU of x3 plus 11 minus b. Soft logic for a Boolean expression. And I have a channel here. Look at this. This is a feature, channel coding right here. And if I look at, for example, x0 and x4, okay, same thing. Look, it's doing the same kind of thing. It's doing feature channel coding for that, right? And the beauty of it is, right, that, if you look at them, yes, they overlap in some places, but they don't overlap in others. So the signal gets through. That's how a neural network is actually coding to do a Boolean expression. Okay? When we saw this, I couldn't sleep for 2 nights. Okay? This is crazy. Okay? Right? So gradient descent is able to find this. Okay? Great. So, cool. Okay, so the codes are only partial. Questions so far before I continue?
Is there any interference that happens from the overlap?
Is there what?
Is there any interference that happens from overlap, especially when you're sort of training it under SDG?
I'm not sure that I understand the question.
So when you say the signal gets through, because there are some routes that are open.
Yeah.
But then
I'm kind of saying that there's a way to I'm claiming there's a way for the network to separate this signal from that signal. The x0 plus x4, if it shows up, I get one thing, right? If x3 and x11 get through, it's another thing, and I can differentiate them, is what I'm kind of saying. Yeah, that's my message.
Can I ask why the overlapping makes the signal harder to pass?
No, it's not that the overlapping it makes it harder to pass, but imagine that I had only one neuron and I had to do 2 features, right? Then, okay, how do I differentiate if I get a signal at the end that is a 1? Is that the 1 because what showed up was x3 and x11, or is that a 1 because x0 and x4 showed up? I don't know. But if I have codes for them, I can separate them because each code is giving me a different signal.
Gotcha.
Okay, those were the positive rows. Look at the negative rows, the ones where I'm getting a negative sign, right? This is saying, no. It's not this, right? What do I see here? Well, what I see is, what it's doing is checking to see if there's x3 and not x11, or not x3 and x11. It's doing XOR. It's trying to see whether or not one showed up and the other didn't, in which case I should give you a negative signal, because then it's not that feature. Okay? So it's coding in the positive in one way and in the negative in another. Okay. Great. So I've got positive witnesses and negative witnesses. Okay, so great. So that's an example, a toy example. Let's do another toy example. Okay? Suppose I have 128 inputs and I want to check whether or not I have 4 in a row in my inputs. Okay? So it's a one-dimensional vision problem. Are there 4 in a row somewhere in this thing? Here's the matrix. Okay, I trained this 10,000, 20 epochs. What do I get? Well, again, good luck. Look at the positive rows. What do you see? You see that it's coding sequences of 4 or 5 or 6. You see it? Like here, and here, and here, and here. And if I actually look, right, what it really is doing, right, is it's actually for every, combination like this, it's using essentially, about 12 rows to code for a given input to see whether or not it actually appears neighboring with another one. And if I look at the negative weight rows, okay, what do I see? XORs. Look at this. It's doing, you see, if these were all kind of sequences of things 4 in a row here, right? When I look at the negative, it's saying, oh, if I got something that looks like this, look, yes, no, yes, no, yes, no, yes, no. Okay, this clearly this is not 4 in a row. Okay? Okay. And what we can do, okay, is automatically look at the codes, right? And just from the correlations, we can pick out, right, what the coding is, right, and try to reconstruct the network from this. Okay? So what I get, right, if I try to do this, you know, with reconstruction of the codes versus the actual matches, this is an example. It's just showing you where it got it wrong and where it got it, you know, I'm running a sequence of tests, and for every one of them, I'm checking to see where there were 4 in a row, right? And here in the actual thing, it says 35, and I say 35, right? If I just built the neural network with the coding that I got from finding, right, what the codes are automatically, right? And you can see here, this one is 40 and I missed it, right? This was 15 and 16 and I got it, and so on and so forth. Okay? Cool. So we can actually figure out the codes for this specific simple case. Okay? So now I want to take us to a kind of a slightly, so if there are any other questions, if not, I'm going to move to something else. Okay? Mind-blowing that the network is doing this. But okay, so what do we know from it? What does it teach us, this stuff? What does it teach us? Okay? So let's try to use this to actually learn something about neural network feature channel coding. Okay? And the way I'm going to do that is as follows. I'm going to take DNFs with 4 AND clauses that have 4 variables. Okay, so for example, if we look at the matrix, there will be something that's like 3, 11, 9, and 13. They are a clause. Okay, that's a feature. Okay, and what I want to do is understand how it's coding. So what I will do is this. I will look for sequences, patterns here. So here's a pattern of 4 in a row. We know that's a way to code for an AND, right? You know, there will be sequences of, for example, 2 that are positive and 2 that are negative, right? Or 4 that are negative, and so on and so forth, right? Or 4 that are positive. So let's look at all these conditions here, okay? And let's try to statistically see what's going on. How is it coding? Because Nir told us that it's coding with 4 in a row, but maybe it's coding with something else, okay? Cool. So what we do is, let's take a network, okay? Let's look at a network of size 32. You can see that I'll take a network of size 32. I didn't say that here. Oh, I didn't say that there also. I'll take a network of size 32, and what I'm going to do is, and this relates back to what you were asking, I'm going to actually start increasing the number of clauses, okay? I'm going to start with 2, and I'm going to go all the way to 64 clauses. So the size of the network is fixed in terms of the number of neurons and the number of parameters, but the number of clauses in my expression is going to grow. In a sense, it's going to be harder and harder to code this thing, okay? And you can see that because you can see if I took one with 32 neurons, you can see that up to 30 neurons or so, sorry, up to 30 clauses, it's still managing to train without error, but after that, it's kind of collapsing, okay? And the 16 network collapses a lot faster, okay? Cool, all right. So what I've plotted here, okay, just look at the one on the right, oh, sorry, on the left, okay? What I've plotted here are the different patterns, okay? 4P, 4N, and so on and so forth. As I increase the number of clauses, well, as I increase the number of clauses. And look what emerges. Oh, by the way, this is in the positive rows, the positive witnesses. Look what emerges. When I'm starting out, right, with very few clauses, you can see that it's coding with a lot of 4P codes. It's putting 4P codes all over the place, right? And as I increase the number of clauses, right, it's using less codes per clause because there are more clauses. So it's only got so much room in the network, right? And so with that amount of room, the number of codes per clause is going down, okay? So it's fascinating to see this kind of thing, right? That it is using these 4P clauses to code for these things. And on the right side, I'm just showing you what random would be. If I just took the same kind of exact matrix, and I did random distribution of 4Ps and so on, right, of all the different types. So what you can see is that as the network, right, as the number of clauses goes up, it becomes harder and harder and harder for it to code. And eventually it's very close to random, right? But clearly, okay, these codes, the training of the network did not end up with a random number of 4Ps, okay? This is clearly doing something that it learned in SGD, okay? Cool. And
this I'm assuming is also dependent on the actual loss function landscape, right?
yes, so of course, almost everything I did here was vanilla without kind of L1, L2, and so on, just to keep clean. But you can do all those other things and learn what it does. Yeah.
And the loss function here is just binary cross entropy.
Yeah. So, and here's an example of the same thing. Okay. Now these are expressions that have one negative variable. And look at this. Now it's coding with a pattern that is 3p1n. 3 positives and a negative looks exactly like the same as the 4p. So because I changed the function, it changed what it's coding with. Okay. Again, looking very different from random. Okay. Okay. So it's coding. Feature channel coding is real. The network is actually doing that. Okay. And we can see that it's deteriorating. So let's try to actually think about scaling laws for a second, which is something we all love because we're training neural networks and we want to conclude things about the small one from the big one and understand what's going on here. Okay.
Could I interrupt one more question?
Yes, please.
So in the previous chart,
Yes.
It seems the model, when it has the capacity, wants to maximally use it.
Yes.
Is that a general trend? It's a
So
typically.
this is it's a very interesting question. So there have been a couple of papers about this, and I just want to say that so gradient descent starting from an arbitrary state, right, will move to some local minimum, right? The optimum would be, for example, if I had 8 neurons and 8 features would be, to just code monosemantically, right? Finding the monosemantic state is probably pretty hard. Its probability in all of the states is low. So we think that it's converging to something that is one of the codes close to where it is, and I'll show something in a second, right? But it's not as if I know. This is a really open question.
These both are very interesting in that regard. That it seems like it tries to find an easier.
It definitely tries to find a code, and it doesn't have a plan B, in the sense that if it cannot converge to a code, then performance deteriorates and crashes, essentially. Okay? If you cannot get feature channel coding, you can't have train the network. We see that, that's for sure. Okay? So success is finding a code.
I'm assuming the choice of optimizer would lead to a different.
You could change the optimizer if you changed, for example, if you did L1, it would change things.
The initial solution might be different.
Totally. Yeah, exactly.
Okay, can I ask a question?
Yes.
So as the number of clauses increase, why does the number of 4Ps decrease? Because
Oh, no, it's per clause.
okay, this
Per
is
clause. The number of clauses is increasing, the room in the network is fixed, and so
so this plot is just for one clause.
this is the average per clause. So this point is 14, on average, I'm coding with 14 per clause. And when I get here, I can only use, whatever, 20 something per clause. Oh, sorry, 4 per clause.
Okay, but the total number of 4Ps would remain.
Yeah, it's actually, it increases to a certain level, yes.
Is it close to optimum? Like you at this kind of like size, you cannot.
You're asking the question that I maybe will answer in 10 years. How do I know? I mean, but
No, not optimally,
Okay.
not optimally theoretically, but you could use like brute force algorithms because this is small enough and you could do.
I'll show you
It's like
something. I don't know. And I would say, oh, go look at my lower bound. But there's so many constants there that it's meaningless.
I see.
Theory is great, but constants matter. Yeah. Okay, so look at this. Look at a scaling law. Okay, let's do a scaling law. Let's fix the number of clauses at 64 for-and expressions over 32 variables, and let's start with a network of size 4 neurons and go all the way to 2 to the 7 neurons. Okay, which is just 128, right? But so I'm increasing the number of neurons and therefore the number of parameters. Okay, and it's the same expression exactly. And look what happens. 4 neurons, they really cannot train to learn this. And as I increase the size of the network, the training and testing error go down, right? And then I ask myself, okay, so I got to the bottom here and it's great. It works really well. What happened here? Well, if you look at the 4p in the positive witness rows and the 3 and 1p in the negative, you can see, first of all, that the coding is different from random. This would be the random number here, right? So there's clearly coding, and it's completely correlated with the error rate. As it manages to actually get better codes, it's improving its accuracy. Phew, I'm like, shit. Shit. Okay. I'm like even more excited than you guys. I mean, this is like, when we see these things, I mean, like, okay, so that's an explanation of what's happening. Okay, that's why scaling laws work. Right? Because before, until now, when we do a scaling law, all we do is we give it more and more and more data, and we hope that it's increasing the number of features, but we don't know. Maybe it is increasing the number. No, here I control the number of features. You know how many features there are. Is it coding, and is the failure to code the thing that is causing it to perform worse? Yes. Okay.
Did you observe any interesting approximate solutions in the dynamics, like as you were tracking the dynamics?
Again, I didn't plan this, but that's what I'm going to talk about now.
Okay.
So I don't know how to analyze it, but let me just show you what happens. We can track things as I train. Why not look at things as they train? Okay, so here's a DNF, 4 clauses, the same thing that I did before. Okay, I'm going to do 20 epochs. Okay, and I'm going to look at the weight matrix as I train. Okay, and I'm gonna expand the first 3 epochs because we found out that that's when most good things happen. Okay, interesting thing. So look, here's the initial state. Okay, this is the layer 2 matrix. Okay, sorted. It's half, positive and negative, but of course I'm pushing all of the positives up and the negatives down. Okay, and I'm sorting these guys based on that, just like before. Okay, random. Yes, random. Okay. 3 out of 3/5 of the first epoch. Something is happening here. It's starting to look like there are these codes showing up here, and there are XORs showing up here. Okay? More codes, more XOR. Okay? Now I'm at, 2 epochs, 10 over 5. Look at this. You see these codes? Right? And the thing, okay? And here, and then this is after 3 epochs, and then here it is after 20 epochs. Look at this. It actually, gradient descent over the epochs, just kind of move things along to get to the coding. Okay? And let's graph this. Let's look at this graph. Here are the epochs, okay? And here is the error going down to 0. Okay, these are the first 3. Look at what it's doing. In the first 3 epochs, 4p is exploding. The number of, it's trying to code 4p patterns as much as it can until it plateaus. Okay? And then once it plateaus, okay, the next thing that is happening, right, is that I'm using the negative guys, replacing places where I have 2 p's and 2 negatives by flipping one of the positives to be negative, so I have 3 negatives and 1 positive, and when I'm done with that, the error goes to 0. That's how it actually converged to an errorless execution. Okay? Now, the beauty of this thing is we can do this for now. We can learn things by running things and looking at what SGD does. This is to answer what you were wondering. Can I control it? Maybe I can. You know, like maybe there are ways in which if I actually knew what codes to look at, I could control the whole process, right? I don't know. Maybe. Okay. Cool.
I think we have a question online.
Oh, yeah.
Do you want to unmute yourself, Mustafa, and just ask?
Yeah, I actually, I think your next slide might answer my question. I was going to ask if all of these observations have only been with a single hidden layer, or if you've explored kind of expanding to
So we are currently exploring more layers, and I'm going to show you the technique that we use for this, okay? We are at the very initial states of this, okay? We have really interesting results, but I'm not in a place to share them yet. But yes, this can extend to deeper layers. I want to show you how we want to do this.
Could I just sort of add a question to that?
Yes.
One thing that is very much of interest to my group here is to understand when we don't have our capacity, when we are memorizing. Say I'm trying to learn a whole book in a language model. When do we not have capacity? So I really like the reason I asked the dynamics question was to understand how do you go towards learning something, but then I'm assuming you probably also have experiments where you realize that, okay, the error went to 0 and now it kept increasing. How did can I look at the dynamics to understand that I'm running out of capacity?
I can totally look at them. I have not done that, but it's super interesting to do it. Any one of the things, my take on this is the following. Any phenomena that you want to understand, okay, right now, clearly it'll be very hard. We don't have the techniques yet to do this on your actual neural network where this is where we're going, right? But you can build a toy model, right, with Boolean formulas and reconstruct something similar to the scenario that you want and understand what's going on. I bet you can. Okay? Yeah, totally. Yes. So how do we go beyond, a single layer? Okay, so to do that, I have to take a moment and actually go back and explain to you how one can look at a neural network combinatorially. Okay, so let's take a step back and look at a combinatorial framework for thinking about neural networks. Okay, so this is a kind of a variation of the work that people have done at Anthropic, and we are just giving it a combinatorial view. Okay, that has to do with our way of disentangling things. Okay, so think of a neural network. Okay, in the abstract. What is a neural network in the abstract? A bunch of features in the input. I have a first layer of a circuit that is a feature circuit, right? Where I get, I take these input features, right, and I map them to a bunch of new features that are combinations of the other features, right? And the same thing in the next layer, I take the features from here and I apply again a combination and so on and so forth, right? Okay. And then I have D of these. That's essentially, from the feature point of view, what the neural network is doing, okay? But of course, there are M0 features here. That number could be 1 billion, right? So I'm not going to have, I'm not going to build a neural network by having it be the size of the number of features by number of features, right? So instead, what we have been doing, what we're training, right, is a different thing, right? I take my very large number of features, right? I embed them somehow, right? If it's computer vision one way, if it's language, I embed them a different way. And now I've embedded them into the size of my input to my neural network, right? And so my first layer, which is doing this calculation, is doing it in superposition. The features are somewhere in there in superposition, okay? And then the second layer, and the third layer and so on and so forth with relevant bias between them, right? That is how I'm kind of approximating this feature circuit with a much smaller collection of weight matrices. Okay? Everybody good on this? Yeah? Okay. I now want to take a different view of the weight matrices. Okay? So this is what we call a disentangled view. Okay? Here's the disentangled view. Every matrix here okay, I'm going to view it as a kind of a, as if I'm compressing here, okay, I'm compressing down from all the features to the space of the number of neurons. The first thing that I'm breaking down, I'm kind of saying my matrix W1 can be thought of as a multiplication of two matrices. The first one is a decoder, okay? It takes the N0 compressed features and expands them to the space of the input features, right, to M0. So it goes from N0 to M0, expanding it, okay? And then the next one takes the input from this, right, and actually codes it back while compressing, okay? So if I think about this, right, so the first thing I do is compress, then I decompress and compress back, then I decompress again and compress back, etc., all the way through the network. And every time that I go, I open it up into this space of the features, then I compress it back down, computing the new feature, right? ReLU of this and this and this and this, whatever it is. Okay? So I'm viewing exactly the same computation that happens here or here, but now I have a different way of thinking about it. Okay? Okay, good. All right, but I'm really interested in this matrix, in the C matrix, in which the coding is happening, where I get the inputs. What I've shown you up till now all the time have been the C matrices, right? Where I get the features and then I tell you what the code is, right? So how do I get them? Okay, so what I'm going to show, because the technique we use, which we call cascading feature disentanglement, works as follows, okay? I am going to use the compression together with the weight matrix that I have originally, the raw weight matrix, the entangled weight matrix, and using I'm going to combine them, and I'm going to get this one. And if I have this one, I'm then going to use it together with the next one to get the next one, and so on and so forth, disentangling it up the channel, okay? Okay, but I still need to show you what is this thing that I do here. Okay, so I'm going to show you what that is. Okay, so here is one layer, right? The first layer of the network, right? So I'm compressing, and then I decompress, and then I have my compressing back, right? Let's just imagine for a second that the compression is just the identity. Okay, all I'm doing is the identity. Okay, so what does this look like? Okay, well, right, what I claim is as follows. What I'm claiming is, oh, Nir, you said this decompresses it, right? It takes the embedding, decompresses it, and then calculates something on it. Great. So if it's decompressing it, then it is the inverse of this thing, right? Or approximate inverse of it, right? Okay. So if I have the matrix W, right, which is the multiplication of these two things, right? And I have the inverse of this, multiply this by this, and I'll get the C. So that's what I'm doing. I'm going to get C1 by multiplying C0 by W1. Okay? So, okay, here it is. Well, it's the identity, so that's not so fair. So here's my matrix W1. Okay, you can see all the encodings here. You can see the positive and the negative, and I multiply by the identity, and I get the identity. Thank you very much. Right? But, okay, let's do this with a Hadamard matrix. Let's train a neural network. I do a Hadamard embedding. I train the neural network. Okay, what do I get? This is what I get. Nothingness. Okay? Right? But this nothingness is actually hiding within it C1. I just multiply this by this, and this is what I get. Look at this. Hiding inside are the codes. This would tell me what the features are. Okay? And so, the thing that strikes me about this is the following, right? Oh, we're going to do magnitude pruning and we're going to remove this weight. But shit, what do I know what that actually means in terms of the actual coding, It could be that I'm removing something very important. A little weight could be the thing that kills my whole thing, right? I don't know. I don't know what I'm doing, right? Okay, and I can do this with a random matrix also. I can do a random embedding, same thing, multiply this by this, and here I get, of course, each one of them is different, right? Because I'm doing a different embedding, right? And I'm doing a different run of gradient descent, but you can see that it's, you basically can expose it. And so you can just do this cascading, and how to do it is really what we're trying to figure out right now. It's complex, okay? I'm not gonna lie and say, oh yeah, we got it all. We don't, okay? But it's an opening, okay? It's an opening to be able to understand sparsification and quantization and how to, all this stuff, okay? Cool. So combinatorial interpretability. I think there's potential here, okay? We can actually, use this to improve our ability to train better, to improve the models, and also, for Red Hat's customers, just, okay, what is this model doing? Okay. And intellectually, okay, the thing that might be the most pleasing is that I see no reason why, actual, animals might not be, feature channel coding. Maybe neurons are doing ands. And it's all just feature channel coding. Okay. Great. And with that, I'll finish.
Thank you. So this is exceptional. I really enjoyed the presentation. So we're gonna open the floor for questions. I think Hal already has his hand up. You wanna go ahead, Hal?
Yeah. And thank you so much for the talk. Really cool result. I have a question regarding the first part of your talk about the feature channel coding.
Yeah.
So I wonder, like for the upper and lower bound you derive, I wonder if you have thought about, assigning like a probability to the class of functions you want the neural network to estimate. And let me elaborate a bit more. So suppose you have, if I understand correctly, so you have a class of functions which could be, like Boolean expression. You want the neural network to compute. So I wonder, among that class, if you can assign a probability distribution to each one of the function within that function class. And of course, that probability will depend on, the number of features.
How often that the feature appears in the expression? Is that what you're asking?
No,
No, you're asking the actual functions.
Yeah, I'm actually asking the actual function.
Right now, I just did this uniformly.
Okay.
Right, but you're saying what if? Yeah,
Yeah. So
you're
yeah.
welcome to take the code and try it out. I mean, I don't know. I don't know.
So
I'm going to say that something will come up. You'll learn something.
Yeah, because I guess my question is more from, so what if we allow the neural network to make some mistakes? Let's say you have an error, and you make the error goes to you make the error vanishing as you increase the number of features you have. Because in channel coding, there's if you allow like a vanishing error, you compared to like zero error channel capacity, you can get way more, send way more messages over the.
You can fit more things.
Yeah, exactly. Yeah.
I think this is something to be proven. My intuition says you're right. That as I relax my requirement, I can get more codes in. Yeah, that's true. Yes. It's not so much that I can get more codes in, it's that I need less to worry about superposition, about overlaps. Mm-hmm. Yes, I think that's correct. Yeah.
Mm-hmm. Got it. Thanks.
Yeah.
William, you wanna unmute yourself and ask the question?
Sure. So does this identify location where features are encoded, or can it also be used to track specific features within the network?
I think the answer is yes. You can find specific features within the network. We have done this only for, we've mostly done this for cases where we kind of know what the features are, but but sometimes things are, I mean, I could show you just because it's super cool. Here's something I didn't mean, I was thinking, okay, if somebody asks a question like you did, then I'll just show this. Okay, look, this is not a DNF, it's a CNF. Okay, so X3 or X11 and X9 or blah, blah, right? And we trained this and we thought, okay, how's it gonna code this thing? And we looked at the positive witnesses and shit, it's just like bland thing. But when you look at the negative witnesses, it's doing some kind of coding in the negative witnesses that looks like the positive that we did before. And when we actually analyze this thing, we realized that what it's doing is applying De Morgan twice to this expression and getting essentially a coding with a DNF that implements the same thing. Gradient descent, okay, finds, for some reason found, this more interesting. So if I go back to your question, right, okay, I'm gonna look at things, okay, and if I know what I'm looking for, maybe I'll find it, but if I don't, right, then, and we've already started doing this, and I gotta tell you, even with Boolean expressions, sometimes we're surprised at what we're finding. So my guess would be that if you looked at a vision, something that's vision or language, it would be mind-blowing what's going on there, okay? But, we don't have the tools yet. We're very far away from the tools to be able to actually look and see where in the network a feature appears that I can actually name and say, okay, this is what it is, Yeah.
Yeah, Brett, go ahead.
Yeah, it seemed like early on there you have you had I don't know if this is an interesting question or not, but it seemed like you have a test for is this number of neurons enough to answer X question, like a certain question?
Yes.
Is that I don't know if that's an interesting question or not, but it seemed like you have a test there early on that you can.
I think you're scaling. I think the scaling law tells you the answer is this thing. So a scaling law is exactly this. Oh, sorry, right? The scaling law says, okay, if I want to do an expression of this size with this amount of error, then I need a network of this and this size. And I can't get away from that. Okay, that's kind of what it's saying. I think this is an opening to build scaling laws where as I train my monstrous 400 billion parameter model, okay, I actually can check it in the small to see what it's coding, right? And then throw it, into the very large thing. And it could be even that the features emerge very early in the training. And all that happens later is better coding, in which case I know what the features are. Hey, shit, now I can just design my training this way. So there are many, many directions to take this, forward if we can actually see the features. Yeah.
Go ahead, William. It's no one in the queue.
Sure. So, did I understand just correctly? So, are you saying that with this technique, then it will be possible to do direct transfer learning from a smaller to a bigger one?
Yeah, I think we might be able to. So here's the thing. I think we're always conflating two things. We conflate the fact that the neural network is learning what the features are, and it's also learning how to compute on them. Right? We do both. The network's doing both of these things. Right? I'm both in my training. I am both understanding what the features. The network learns what the features are. Right? What are the features for a cat? What are the features for a dog? And then it's also learning how to compute cat and how to compute dog. Right? But imagine that very early in the training, I see all the features for cat and all the features for dog. Right? I can hand code a better neural network. Why do I need to go through the suffering of training, right? Maybe I can just hand code it, right? So there's a lot of potential there to kind of separate the feature detection from the execution, right? Maybe a 400 billion parameter model, if I actually trained it and got the features, I can do it with, 10 million parameters. Just those same features. Who knows?
So I had a question. When it comes to transformers in the NLP, a very common pattern is you have matrix, and then you expand like the number of
Right.
dimensions, and then you apply like a gating function and you expand that down. Have you like had a chance to look at how what
No,
that's doing?
we started talking to the Anthropic guys this week to see if we can actually, because we think that one way to do this is with autoencoders. There is possibly a way to use autoencoders to actually do this kind of thing, actually on transformers. But we're gonna try. I think this is very early days. Yeah, maybe yes, maybe no. Yeah.
Professor, how do the bounds that you showed earlier change when there are more than two variables per class?
So the bounds that I showed there, right, are for features. So I'm not saying how many variables there are in a feature. It essentially has to do with what a feature, right? So if you want to think about it, right, then features don't really care how many variables kind of there are. There's a certain representation for it in terms of bits. I don't know, whatever that is. And essentially, the bound is talking about relative to the number of bits there. Yeah, so what this is, it's also saying, right, if I need a certain number of bits to do something, then if I quantize it to 4 bits or I quantize it to 8 bits, it's actually saying, oh, actually I can get a lot more, which is kind of what we know. Yeah.
Awesome. We're at time. Thanks again. Yeah.
Thank you, everybody.